everyone. My name is Badrine Chirabo. I'm going to be taking you through machine learning, what I know about it. Yes. The first slide has my details, my name, Chila Madrin, my SIN number, registration number, my colleague's details, and then the date. So what is machine learning? Well, how I understand machine learning, it is a field of study that gives computers the ability to learn without explicitly being programmed. So the key idea here is the computers being able to make decisions through the patterns of the data. What you mean by this is that you do not have to write a proper computer program. But if a computer is given such a data set or such a data type, and it is required to make a decision, you do not give it that decision it's supposed to conclude to, but rather you teach it or you give it time through training, and it gets to learn through the patterns or the features that the data has, and it gets to know the kind of decision it can make depending on the data that it has been provided with. Okay? There are two types of machine learning. Oh, sorry, I forgot to give you some examples of machine learning. It can be applied in like classification of emails. Let's say you want to separate the spam from the real email, you can use machine learning. And also the autonomous cars, you can use machine learning. So there are two types of machine learning, and that is the supervised machine learning and the unsupervised machine learning. I'll talk more about the types later. In the next slides. So we are going to engage with various terms, but of course there are key concepts in our course. In machine learning, particularly, there are concepts like a model, a data set. We're going to be seeing them more often. And how you can define a model is by saying a model is a representation of some phenomenon. A phenomenon can be anything, because depending on the problem you have, that will dedicate the kind of data that you give the computer. So the representation of that phenomenon is what we refer to as a model. And there are two types of math models, that is the deterministic and the probabilistic. So in deterministic, of course, there is no randomness because it can be determined, whereas in the models that involve probability, there is randomness because probability, you don't know the likeliness of something to happen. So the chances can be high or low in the probabilistic models. So we're now going to see the types of machine learning in detail. We have supervised machine learning and the unsupervised machine learning. So in supervised learning, the data set is labeled by the humans, or let's say the data set that is used in the supervised learning is labeled. If you have data that is labeled X and Y, the goal would be to map the inputs X to the outputs Y. And the result is the necessary supervision to give the machine learning algorithm when it's training. You do not let the model learn by itself completely, but the result is that necessary supervision that is required as the model trains. That is what is in supervised machine learning. And there are algorithms that I used to deploy my supervised machine learning, and we include regression, we have decision trees, we have classification, and let me talk about regression briefly. Regression uses numerical data, and it's always continuous, like something that has to do with values, and it's continuous. Let's say the price of a house, the amounts, like figures that are continuous. And when you have such kind of data types, you always use regression to like the regression algorithm of supervised learning. You get it? And then there is classification. And in classification, it is used when the data you have is of categories. Let's say you're dealing with gender, when you have two genders, male and female, of course there are categories. So if you have categories, that is when you use the classification. That is some of the knowledge I tried with supervised learning. And then for unsupervised learning, the data sets that I use here are unlabeled. The data is not labeled, but there are features, it has features. And the goal is to define patterns or groupings in the data. The data is not labeled like the way it is for supervised learning, but there are features that can help the computer to identify or make decisions. For example, if you're teaching a baby how to differentiate between a cup and a glass, of course, you may not follow the patterns, but you use the features. Let's say a cup has a handle and a glass may not have a handle. Maybe the glass is breakable or something like that. Okay, use features. That is for the unsupervised learning. And then the algorithms that can be deployed in unsupervised machine learning. We have clustering, we have clustering and principal component analysis. We have anomaly detection. So let me briefly talk about it here. In clustering, all that you have to aim on is to group the data features together that exhibit similar characteristics. If you have data features that have or exhibit similar characteristics, you go ahead and group them together to form different clusters. That is what clustering is. And then for the anomaly detection, it involves detecting unusual occurrence of data instance in a data set. If you see something unusual in the data set, you always use the algorithm of anomaly detection to help you detect that instance in the data set. In my colleague, we'll talk more about the PCA, the principal component analysis. Let me proceed. So, of course, in any learning or in anything that involves learning or getting to know about something or acquiring knowledge requires you to follow a process, or it's already sequential, or it's systematic that you need to go like from the head. So something of a sort. So in machine learning, of course, there are steps, and these are some of the steps that are involved. You go ahead and define the problem. Let's say you want to go ahead and deploy a system or a machine that's maybe a biometric scanner or a biometric stamping in something that workers can use when they come to work. That could be a problem of like solving the problem of attendance, because some of the workers may be like, no, I came at this time. But when you use a biometric scanner or a biometric stamping, of course, it will always show the time you stamped in, the time you came. So that could be a problem you're trying to solve. So you need to define the problem, go ahead and collect, and then process the data. Sorry about that. You go ahead and collect the data that is connected to the kind of problem you're going to solve. Choosing and training the model, you go ahead and make the machine or the model familiar with the kind of data it's going to be making decisions from. Then evaluating and tuning the model. So after you train the model, you then go ahead to evaluate it to know like, will it be a success? Will it be successful? Something like that. Evaluating comes from the results, or like how long it took for the model, or the accuracy, or how close it was to get to the answer. Then if it was successful after the evaluation, or if it was close to being successful, you can go ahead and deploy the model. We went ahead and broke down all the key steps in machine learning in detail. So this is data collection and pre-processing. The sources of data can include the application programming interfaces. The short form is the APIs, the databases, web scraping. So for example, for the biometric stamping in at the workstation, or maybe at school, of course, the data will always have to be retrieved from the database, because all the workers, the students, all the agents that are involved with that model or computer or machine are always in the system, they're always registered in the system or in the system already. So when someone comes and then the model is able to identify them by their features or characteristics, it's able to retrieve data from the database. In that way, a database acts as our data source. That's the way it is for web scraping. Data APIs always have the information that you need to know about different applications. So data collection includes feature engineering and cleaning of data. Cleaning of data involves handling missing values, duplicates, and noise. Whereas for the feature engineering, it includes scaling, encoding, and feature selection. We're going to see more about this in the next slide. So feature engineering is basically creating meaningful input features from raw data. Let's say you've just been like giving raw facts to the model. You now have to make it meaningful. Well, she's a girl or she's female, but what makes the data more meaningful. That is what we mean by feature engineering, making it more meaningful, not leaving it just as raw facts. You go ahead and add more information or add more data that makes it more meaningful. By doing that, you're doing feature engineering, or we are doing feature engineering. So some of the techniques that are involved or are included in feature engineering is scaling, encoding, and feature selection. In scaling, we go ahead and normalize and standardize the features. You normalize the features and standardize them, that this person's face is supposed to be like this, or it's supposed to look like this. Anything that is not like this, do not verify that this is the person, or if someone's tongue is different from this, then that's not a person. That is where standardizing the features is. Then encoding involves converting categorical data into numerical facts. For example, I give you that example of classification. Let's say you're classifying girls and boys. So you go ahead and convert that categorical data into numerical formats. Like how many girls do we have? How many boys? If we're employees, how many work as a male? How many are female? How many can do IT? How many are doctors? Something like that. You convert it from the category data into the numerical format. Then feature selection, you choose only the most relevant variables, only the most relevant. Let's say on someone's face, and it's going to be a biometric facial recognition. It may not be necessary to scan all the features like on someone's face, but of course, maybe to pick the iris of the eye. Then it also picks the spacing between the eyes, the position of the nose, something like is significant, something that is relevant. Yeah, that is what is feature selection. The importance of feature scaling is that a good feature improves model performance. And my colleague will take on from that. Thank you.
My name is Guy Edward, and I'll take us through the rest of the video, starting from where my colleague stopped. I'll start with linear regression as one of the common ML algorithms. Linear regression is a supervised learning algorithm for predicting continuous dependent variable using one or more independent variables. In other words, linear regression predicts an output given one or more inputs. For example, when we want to find the prices or the price of a house as our output, we can use a variety of inputs such as the size of the house or the location of the house. And the line of best fit or the best fit line helps us to minimize errors between the predicted and actual values. And this is a line that is drawn after plotting a graph of dependent variables and independent variables. I'll talk about logistic regression. It's a supervised machine learning algorithm used for binary classification problems. It predicts the probability of an event occurring, and its outputs are a Boolean value, which is either a 0 or 1. How this works is that when you get a real value and you map it to a certain value between 0 and 1, and it uses a threshold value to know if the value is either 1 or 0. For example, we can use a classification problem such as spamming in messages. Now, if the probability that the message is a spam is 0.8, that value is about the threshold value, so it tends to a 1, so the message is a spam. If the probability that the message is a spam is 0.3, that means that value is below the threshold value, hence the message is not a spam because it tends to a 0. Next, I'll talk about the KNN, which is the k-nearest neighbors. It's a simple non-parametric machine learning algorithm used for both classification and regression. I'll use the graphs provided. I'll use the graphs in the slides to describe it. In the graph before KNN, we have a new data point, which is blue, and we have data points that are categorized into A and B. Now we want to find the nearest neighbor, so we measure the distance between the nearest point from category A and the nearest point from category B. Now, if the nearest distance is between the new data point and a point in category A, that means that point belongs to category A. And we use the Euclidean distance to find the distance, or the Manhattan distance to measure the distance. Commonly, those are the methods used. One of the applications of KNN is text mining, agriculture, finance, and many others. I can talk about finance. Banks use KNN to determine the risk of giving out loans based on credit card system, and I provided a link to a research paper of how that is done. One of the main pros of KNN is that it's easy to explain and simple to understand, and it's extremely powerful. And one of the big downsides of KNN is because the efficiency of the algorithm declines as the data set grows. Plus so many other disadvantages, like it comes at a cost of making a prediction step relatively expensive. Next, I'll talk about decision trees. Decision trees are supervised learning algorithms used for both classification and regression. Now, a simple example of a decision tree is determining whether someone can take coffee or not. Now, the most important part of the decision tree is the first question, the initial question you ask yourself. Now, for this decision tree provided, the initial question, which is one of the most important questions, is the time of the day. Now, you ask yourself, what's the time of the day? Is it morning or afternoon? If it's morning, is the person tired? If he's tired, yes, then you can drink coffee. If he's not tired, then no, you can't drink coffee. If it's afternoon, you check if the person tired or not. If the person is tired, then yes, the person can drink coffee. If he's not tired, then no, they cannot drink coffee. As you realize, decision trees are very good because they keep breaking down the data into smaller and smaller compartments. And one of the other pros of decision trees is because they're easy to interpret and visualize. And one of the downsides is because they are sensitive to noisy data and they can overfit noisy data. Next, I'll talk about ensemble learning and random forest. Ensemble learning is about combining many weak models in one supermodel. And random forest is an ensemble learning method used in bagging that uses matplotlib decision trees to improve accuracy and reduce overfitting. Sorry. One of the real lifetime examples I can give is when you're planning to go for a trip and you want to ask a couple of your friends for the ideas. After asking your friends for the ideas, you can sum them up, and see which idea was most given, then you go by that. Or you can aggregate the ideas and you choose your best outcome. So putting it in a machine learning context, we can have a training data instance. Now, with that training data instance, we form multiple decision trees on which you have to train each of them, and each of them is supposed to provide or give an output independently. Now, using bagging, we find the overall best prediction using each of the decision tree outputs. And one of the issues with this is slow training, because training each and every decision tree is slow. Whereas on the other side, it's advantageous because it works very well with nonlinear data, lowers the risk of overfitting, and is robust to outliers. Next, I'll talk about the support vector machines. There are supervised learning algorithms used for classification and regression. Now, SVM aims to find the optimal hyperplane that separates data points from different classes with a maximum margin. I'll talk about this. Using the graphs provided, when you have two data inputs, your hyperplane is just going to be a single line. As opposed to when you have multiple data inputs. For example, if you have 3, your hyperplane will be 2-dimensional. And when we talk of maximum margin, we're saying that the line in between the two data inputs should be having a distance, the maximum distance from the neighboring data point on each side. One of the pros is because they are robust to outliers. Using the second graph, you can see that the blue data point is an outlier, but it is ignored. And then we shall have our line, our hyperplane, as you've seen there. And they work very well with large data sets, and they lower the risk of overfitting. And some of the constraints, they are biased with categorical variables, and they also have an issue of slow training. I'll talk about the principal component analysis next. And the goal of PCA is to reduce the dimensionality of data while keeping the information loss to a minimum value. Now, with time, you notice that the dimensions of the data keep increasing. Like the input features that must be taken into considerations become so many that it makes the computability of the algorithm very hard, and finding the output very difficult, and developing algorithms to study the data set very hard because of the very, very many input features that must be put into consideration. So that's where PCA comes into handy, because it reduces the dimensionality of the data. So it assumes that the variables are linear correlated. That means it assumes that the variables are related to each other. Now, if the correlation is not linear, then PCA will not be efficient. So some of the pros is because it's simple, powerful, and works for both regression and classifications, and no assumptions on data distribution. And some of the cons are inefficient with large data sets, and sensitive to missing variables and skewed class distributions. The applications of PCA, the main applications of PCA, which have image compression, preprocessing for classification, regression, and cluster tasks, facial recognition, that's gene faces, and data visualizations. In conclusion, talk about machine learning transforms data into actionable insights, algorithms like K-mean, random forests, and PCA cater for varied use cases. Preprocessing and feature engineering are vital for model access. Then design methods like boosting and bagging enhance model performance, and real-life applications like span, finance, agriculture, image processing, and more. Thank you for listening to me. Have a nice evening.